Yep. Okay, we're all ready. What happens is that the secretary will do his stuff. Right, good evening everybody, welcome to our March meeting of the Astronomical Society of Glasgow. So I will call on David to give us the secretary's announcements.
Thanks, Robert. Okay, just a few things happening that are coming up. The first event is taking place next Tuesday. This is a members event. It's a night at our own observatory, Edinburgh. That takes place from around about 7 o'clock to 9 o'clock. So that's next Tuesday, 25th of March. As I said, it's for members only. The next event takes place a couple of nights afterwards. A week tonight is the next meeting of the imaging group, which is an online meeting held via Zoom from 7:30 to 9 p.m. I have some information here about it. The next imaging group Zoom meeting will take place on Thursday, 27th March at 7:30 p.m. with ASG member Ian McFadden will give a presentation on the processing of planetary images following his recent very impressive images of Jupiter. Members will then be invited to ask questions, and then the meeting will be opened up to the floor of the other members. A Zoom link will be sent out. And finally, the Society will be running a free public event at Edinburgh between on next Saturday morning to coincide with the partial solar eclipse. This takes place between 10 and 12:15. First contact of the moon on the sun is at 10:08 and the last contact is at 12:07. It's a free event, so just turn up. There's no days, so the following Saturday, Saturday the 29th of March. So there will be telescopes there, specially filtered telescopes. They'll be available for members of the public to observe the eclipse. I think there'll also be a few smart telescopes as well. Maybe some chance to do some video imaging as well. So, as I said, no booking, just turn up on Saturday morning. That's it, Robert.
Okay, so that brings us on to the main part of the meeting tonight. We've got Dr. Ben Giblin from the Royal Observatory Edinburgh, what's it called, the UK Astronomy Institute, or the Edinburgh
all the organisations there,
and Ben is involved in the Euclid Space Telescope, if I pronounced that correctly. And he's researching dark matter, so he's going to give us a talk on shedding the light on the dark side of the universe with gravitational lensing. Okay.
Super, thanks. Can everybody hear me okay at the back? Okay, yeah, thanks very much. I'm thrilled to be here. I'm going to be talking about shedding light on the dark side of the universe. So this is the side of the universe that is not directly observable. This is the side of the universe that is invisible, and we need other sort of out-of-the-box ways to kind of infer the properties of this side of the universe. And the way that I specifically do this is with gravitational lensing. So I'm going to be talking about that. Okay, so this is a talk on cosmology. So if you don't know what cosmology is, It's basically a branch of astronomy that is concerned with how the universe formed, how it's evolved over billions of years. And this inevitably becomes a study of what the universe is made of, basically, on the whole. Because what it's made of determines how it behaves, how it evolves, how it will continue to evolve in the future, and how it formed. So this is how I kind of see cosmology and where it is at the moment. I think we're at a crossroads, and we don't really know which direction to go. And the reason for that is that we have sort of some real conundrums in cosmology at the moment. So one of the things that's keeping us up at night is the fact that dark matter and dark energy remain a complete mystery. So these are two really important ingredients of the universe that have a huge impact on how it evolves over time, and we really don't know what they are, like on a fundamental level. Another thing that's really kind of a big head-scratcher in cosmology at the moment is the fact that numerous cosmological surveys conducted by people all over the globe, independent teams, observing different eras and epochs of the universe's evolution, they should all be getting the same answers, and they're not, essentially. They're returning results which disagree with one another. That could be because those analyses have mistakes in them, or it could be that another solution is that there's a serious misunderstanding or something missing from our basic picture of how we think the universe has evolved. So we're at this sort of really interesting time in this field. So I'm going to talk about where we're going in this field, but also how did we get here. Okay. If you only take one thing away from this talk, I hope it's this. Cosmology is a piece of cake. And the reason I think that is because if you were God and you were going to create a universe, you would need two things, right? And they are the same two things you would need if you were going to bake a cake. So let's imagine we are God and we want to create a universe. What we're looking to create is something like this picture on the right-hand side. This is the large-scale structure of the universe, sometimes called the cosmic web, because it kind of looks like a big spider's web. Basically, this is structures that measure billions of light years across. They are the biggest things in the universe. And the bright sort of intersections of all the strands of this web, they are the most dense regions in the universe where you would expect to find massive galaxy clusters. And then along the strands of web, you might find more galaxies and loads of gas and dust, essentially. And all these dark regions are empty regions of the universe, sometimes called cosmic voids. So this is what we're thinking about when we think of what the universe looks like on the whole. Did I say this is not the real universe? It's a simulation. So yes, but yeah. If you were going to create this, you need two things, the same two things you would need if you were baking a cake. The first thing you would need is a recipe. Okay? So if you're baking a cake, you've got a recipe, it tells you how much flour, sugar, eggs, etc. go into it. If you're going to create a universe, the recipe you would need is a description for the laws of physics in that universe. Okay? So there's lots of laws of physics at play in our universe. You know, you're often quoted that there's 4 fundamental forces, 2 strong and weak nuclear forces, and then there's electromagnetism. But when we're thinking about the large-scale structure of the universe, this thing, the most important force, the one that has the biggest impact on the structure of this thing, is gravity, which is why I've done a screenshot of Albert Einstein's original paper on general relativity. So this is the leading theory of how gravity works. So this is from 1915. So we think we know how gravity works, right? This is our recipe for how this big structure grew over time. It grew through gravity. So this is our recipe, Einstein's theory of gravity. Normally, when you're baking a cake, though, and you've got a recipe, that recipe tells you how much of each ingredient to put in. You know, it tells you how many chocolate chips and how many eggs you need and how much icing sugar. General relativity isn't really like that. And I'll get on to that in a second. So that's the first thing you need. You need a recipe. The second thing you need is ingredients. And ingredients determine the output, right? If you look at this picture on the left-hand side, you can already see that these are not the ingredients of like a shepherd's pie or haggis, neeps and tatties, right? This is gonna make only a limited range of things. It's probably gonna make a cake, this kind of thing. But depending on the proportions of each ingredient you put in, you could make different types of cakes, right? You can make chocolate, you can make I don't know cakes that well. But you can make a few different types of cakes. So what are the ingredients of our universe? So as I just said, general relativity, it's not the most prescriptive recipe because it doesn't tell you how much of each ingredient to add. So it's kind of a bit like the recipes that they get in the technical challenge at the Great British Bake Off. I don't know if you watch Bake Off, but there's usually a challenge where they're tasked with making something they've never seen before, and they're just given the ingredients, but they don't know how much of each thing to add. The recipe doesn't tell them. It's, you know, a test of how good a baker they are. That's what it is like in our fields, because general relativity has some ingredients in the equations, but when it comes to our actual universe, the theory doesn't tell us how much of each ingredient went into making the universe we live in. Okay, so that's basically something we have to figure out as cosmologists. So cosmologists sat down and they wrote a list of the ingredients of the universe. So these ingredients are basically 3 parameters in our recipe. And our job as cosmologists is basically to figure out what the values of these numbers are in the actual universe we live in. So I won't go through all of these, but just to give you a flavour for some of them. The first one is the Hubble parameter. So the Hubble parameter is basically a measure of the rate of expansion of the universe. It's also kind of related to the age of the universe. You've got the total matter energy density, omega n. This is basically how much matter is in the universe. And then we also have another parameter, which is the amount of baryons in that universe. So baryons are the matter that we're all made of, protons and neutrons. It's everything in the periodic table. So you can think of baryons as like the ordinary matter, basically. And if that's the only type of matter that exists in the universe, you would expect this omega n and this omega b number to come out exactly the same when you do a cosmological survey. Spoiler alert, they don't. Okay. Another ingredient is the cosmological constant, omega lambda. So this was a term Einstein introduced to his theory of general relativity, and he regarded this as his biggest mistake ever. The reason he introduced this term was kind of out of prejudice, because he looked at his equations and he recognized that if gravity is the only force affecting the large-scale structure of the universe, then there's nothing to stop that universe collapsing. Like gravity pulls things together, right? So he didn't like that idea. He wanted to create a universe that was static, where gravity is perfectly balanced by something else that's working in the other direction. And then we'd have a sort of static universe that was ageless and has been around forever. So that's why he introduced this cosmological constant. It was the right thing to do, but for the wrong reasons. So essentially, cosmological surveys have found that this thing really does exist. Einstein later regretted it and was like, that was probably stupid. No, it was correct. It does exist, but it's a lot bigger than Einstein thought. Okay, so won't go through the rest, but these are our ingredients of the universe. So it's our job as cosmologists to figure out what the values of these numbers are. So it's kind of like, to use the cake analogy, the cake has already been made and it's been put in front of us, and we've got the recipe, but we don't know how much of each ingredient went into it. So we're looking at it thinking, yeah, there's probably this much sugar, this much chocolate, okay? That's kind of, that's kind of our day job. And it leads to results like this. So this is, probably seen a pie chart like this before, called the cosmic pie. I like to call it the cosmic humble pie, because cosmologists were a bit embarrassed about this. So essentially what this chart is telling us is that more than 70% of the universe is this thing called dark energy. This is basically kind of the new branding for this cosmological constant. This is this thing that works in the opposite way to gravity. Instead of pulling things together, it pushes things apart. And this seems to make up the majority of stuff in the universe. So by stuff, we kind of mean energy. And it makes up, more than 70% of the universe. Then we have this other ingredient, dark matter. So this is matter that is completely invisible. It doesn't seem to behave at all like ordinary matter or interact with the world via electromagnetism, the way that the particles that we're made of and all human experience is made of doesn't behave that way. So then that basically means that the stuff we do understand, these heavy elements, this hydrogen and helium, these things called neutrinos, that stuff makes up less than like 5% of the universe. So this is quite like embarrassing for cosmologists, because our job is to figure out what the universe is made of, and we come to the conclusion that we don't understand 95% of our job description. Yeah, I mean, like in no other industry would that level of incompetence be tolerated, outside of American politics, of course. So, how did we get here is the question. Okay, and where is here exactly? So, this picture I've shown you, it's formed what we now refer to as the standard model of cosmology. That the nickname for that model is lambda CDM, where lambda is that cosmological constant. You can think of that as dark energy, and the CDM stands for cold dark matter. So we name it after the stuff we don't understand, basically. And yeah, this model is built on Einstein's theory of gravity. So this is our recipe for the structure of the universe. How did we get here? Well, one of the biggest pieces of evidence for our standard model of cosmology comes from the cosmic microwave background, and that's what you're looking at here. So this is the microwave radiation left over from the Big Bang, and this is everywhere on the sky in every direction you look. And what you're looking at here specifically are temperature fluctuations. And these temperature fluctuations, they might look large from the picture, they're actually really, really tiny. They're at the level of like a 10,000th of a degree. And as you look from left to right here, what you're seeing is how the resolution with which the cosmic microwave background, or CMB, has been imaged has improved over time with various instruments, from something called COBE in the early 90s to WMAP in the noughties, and finally the Planck satellite, which is this little guy in the right-hand corner. Why is the CMB important? What's so cool about it? Well, essentially, when you image these temperature fluctuations, what you're seeing is a battle map that shows a war being fought between two forces. Okay, so in the red spots, these are the hot spots of the CMB. That's where gravity is winning. So gravity is succeeding in pulling particles together, creating overdense regions which are a little bit hotter compared to the average. In the blue regions, the opposing side is winning. And that opposing side is radiation pressure. So this is the pressure that stops, my hand going right through this table. It's because there's particles in the table that repel the particles in my hand. These forces do not want to let particles get too close together. So this is what these temperature fluctuations are telling us. The reason that they're really cool is that this is a blueprint for the large-scale structure of the universe. When we image the CMB, we're seeing the universe as it was when it was only a few 100,000 years old. No massive structures had formed yet. But these hot and cold spots, which are regions of slightly higher density and higher temperature, slightly lower density and temperature, these grow over time. And these form that large-scale structure that I showed you before, millions of years into the future. So what you're seeing here is the early blueprint for the large-scale structure of the universe. So we can use this map to tell us what we would expect to see in terms of large-scale structure, and therefore what were the ingredients that went into making that universe, the one we live in. So, in order to do that, you need a way of quantifying the information in this map, right? So, essentially, you need a way of summarizing all of this amazing information and then comparing it to a prediction which comes from our recipe, from Einstein's theory of gravity, and then we can try to figure out what the ingredients of our universe were. So the way we summarize all of this amazing information is with something called a power spectrum. That's what's plotted on this map. It's fairly kind of straightforward. The y-axis basically tells you the strength of these temperature fluctuations, and the x-axis is the angular size of those fluctuations on the sky, where this end of the plot is smaller angles, this end of the plot is larger angles. So these blue points, those are the actual measurements from the Planck satellite, which is the map on the far right here. So that's the real universe. And then this red line that goes through all of those points perfectly, that is the prediction that comes from our recipe. So the exact shape of this line, it does depend on those three parameters that I showed you before, these things. So what we've done is we've fit for these three parameters until this line went through these data points. And that's how we get the values of these parameters, and we figure out essentially how much of each thing went in to making our universe. And really the thing to take away here is this line fits these data points like perfectly. It looks so good, this fit. When cosmologists saw this for the first time, you'd be forgiven for just going, we have done it. Like, we have the recipe right. We know how the large-scale structure of the universe has formed, and we know the ingredients. And these are the ingredients. So this is what this measurement told us. First of all, it could tell us the values of this omega lambda, how much dark energy there is, and omega matter, how much matter there is. And what they found is that dark energy dominates over matter by about a factor of 2. So that's where you get that 70% part of the pie chart you saw before. And the other thing it told us, which is kind of exciting as well, is that dark matter makes up the majority of that matter in the universe. So this was evidenced by the fact this omega B parameter, that's how much normal baryonic material is in the universe. And you can compare that to this omega C is how much cold dark matter there is in the universe. And the dark matter number is about 5 times larger than the baryon number. So essentially, there's 5 times as much dark matter in the universe as there is ordinary matter. So that's why dark matter makes up such a big part of that pie chart before. And the other thing this tells us, which is pretty cool, is that there was a Big Bang, basically. The other thing you can measure from this is the age of the universe, and it comes out at 13.8 billion years. So yeah, as I say, you could be forgiven for looking at this and just thinking, cosmology is over. This shows we've got the recipe right, we know the numbers, okay, we still don't know what dark matter and dark energy is, maybe some particle physicists will figure that out, but you know, we can go home, right? Unfortunately not. Well, I should say fortunately, because this does keep me in the job, but cosmology is far from solved. Why is it far from solved? We have these cosmic tensions. So this is that thing I was saying about all these different teams of cosmologists around the world. They're getting answers that don't agree with one another. So on the y-axis here, you've got that Hubble parameter. This measures the rate of expansion of the universe. And on the x-axis, you've got the year in which different surveys publish their results. And the blue points come from that cosmic microwave background measurement I just showed you. The red points come from something else. They come from using supernova explosions to measure the rate of expansion of the universe. That's another way you could estimate this parameter. And you can see these things used to agree at like the turn of the century, the millennium. But as you go on, the blue points and the red points start diverging, and now their error bars no longer agree. And now the difference between the blue points and the red points is massive, as the error bars have got smaller and smaller. This could mean that there's some mistakes have been made in one of these analyses, because you're both looking at the same universe, you should get the same answer, but they don't. So it could be that someone's just made a mistake, like there's a mistake in someone's code somewhere. However, this could mean that the recipe is wrong, like the Einstein's theory of gravity, the standard model of cosmology, that there's something missing from it. It's not the only tension that exists. This is another tension. So on the x-axis here, we've got that amount of matter in the universe again. The y-axis here, that measures basically how clumpy the matter in the universe is. And the little red circle, again, comes from the cosmic microwave background measurement performed by the Planck satellite. But then you've got these three banana shapes, and these bananas, they come from a different cosmological probe called weak gravitational lensing. And this is what I do weak lensing. So I'm going to talk about that. Before I do, I added one slide today, so if anyone's read BBC News this morning, they will have seen this article about dark energy experiment challenges Einstein's theory of the universe. This is another sign the recipe could be wrong. What this article is referencing is this result, which came from a team called the Dark Energy Spectroscopic Instrument Collaboration, or DESI. They're actually measuring things like how galaxies cluster together, and that is one way of measuring this cosmic web. And what this result is showing on the x-axis is a parameter that tells you something about how dark energy behaves today, and on the y-axis is a parameter that tells you something about how dark energy changes over time. So in Einstein's theory of gravity, basically this was the one ingredient that the recipe actually told you the number for. Like it said, dark energy should have these numbers. And the reason it's called the cosmological constant is because dark energy wasn't supposed to change over time. It was supposed to be this constant level. So this thing that measures how it changes over time, it was supposed to be 0, which is up in the top left-hand corner of the plot. And this other number, W0, that was supposed to be -1. So where those two dotted lines cross, that's what Einstein's theory said the answer should be. But this green sort of contour here, that is the measurement from the DESI collaboration. And the sort of size of this indicates the uncertainty they have. It doesn't go anywhere near the point on the plot which would be, Einstein's view of this parameter. So this is like a massive deal in the field at the moment, basically. Is dark energy evolving over time? that would be a major crack in our standard model of cosmology. Okay, but I said I would speak about weak lensing, and that's what I'm going to do now. Okay, so gravitational lensing. How am I doing for time, by the way?
You're fine. Wait, it's
Super
just-
duper. Cool, so gravitational lensing. Maybe you've heard of this before. This is a little video to illustrate the concept. You've got a distant galaxy on the left-hand side. We're over here on Earth on the right-hand side. Let's press play. The galaxy is throwing out rays of light, but between us and that galaxy, there's a massive compact object like a galaxy cluster. And that galaxy cluster, because it has gravity, it's bending the path that those light rays take, and that causes the image of that distant galaxy to become distorted. And in this case, that distortion is really strong. You can see it by eye here, like these sort of arcs of light on the sky. That's actually just like one single galaxy. That should appear like, a little point, but it's being stretched out into these big arcs. So it's kind of like viewing a candle through a wine glass. It basically, because the light bends as it passes through the wine glass, it distorts the image of that candle as you see it. So here, this gravitational lensing, as we call it, is really strong. So we call it strong lensing. Oh, here's just another example of a cheeky, mischievous smile, where the smile is again made up of these arcs of light, which is the light bending from the background object. But this is really strong lensing. Strong lensing. That's not what I do. So I do weak lensing. The reason we do weak lensing, where the distortion is much smaller than this, is because this type of strong lensing thing, that only happens at sort of individual sort of pinpoints on the sky, where there's something really dense along that sight line. It doesn't happen in many places on the sky. Weak lensing, on the other hand, happens everywhere across the sky. So here's a little image to try and illustrate some weak lensing. So this is another simulation. This sort of weird tinsel-looking stuff, that is that large-scale structure of the universe, that cosmic web. It's made out of big filaments of dark matter and galaxies and galaxy clusters. And it's everywhere in the universe. It's in every direction you look. So on the left-hand side, those little blue dots, those are galaxies. And then these orange things are the light from those galaxies. As it passes through the large-scale structure, it is lensed continuously as it's traveling. It's being deflected continuously. And if we take a look at this thing from the right-hand side, so we're looking down the box, it kind of looks like this. So you can see that cosmic web. And what we tend to see is the galaxies, which are all these blue things, the shapes of them are distorted a very, very small amount. And also they start to line up with one another as well. So their shapes and their orientations change. But yet, the impact on an individual galaxy is really, really small. That's why we call it weak lensing. Another way to explain this, I suppose, is this kind of image. It's kind of like we're looking at coins at the bottom of a well. And so the coins are the galaxies, and the water here is this large-scale structure, which is mainly dark matter, because dark matter, as we've seen, makes up most of the matter in the universe. So we're seeing distorted images of those coins. And by the way, dark matter, it's a really rubbish name, because it implies that that matter is darkly coloured. In fact, it's transparent, so it should be called transparent matter, really. So that's why I quite like this idea, because water's transparent, right? But you can tell it's there, and you can tell it's there because it bends the light from something that's on the other side of that water. So that's how you can tell you're looking at these coins through a body of water and not just looking directly at them. Okay, so as I just said, weak lensing of these galaxies, it's really small and basically impossible to detect for an individual galaxy. So what that means is we actually have to take images of millions of galaxies. And when you take images of millions of galaxies, even though the distortion on an individual galaxy is tiny, if you start to do statistics with that sample of galaxies, then this lensing effect starts to add up and it starts to become detectable. If anyone's actually into statistics, this is basically my whole job. What we're actually looking for is correlations or patterns in these galaxy shapes across the sky. And if galaxies are really far away from each other, they shouldn't really show any correlation or any pattern. The only way that would happen is if their light has travelled through the same structure along that sight line, and that induces patterns in them. And so that's what we're looking for. We're basically looking for statistical patterns in galaxy shapes. That tells us this lensing has happened. Why is this useful for cosmology? The more matter there is in the universe and the more strongly it clumps together, the more lensing there is. So we try to measure how much lensing has happened, and that tells us kind of those numbers, those ingredients of the universe. And it can also tell us something about the rate at which the universe is expanding, and tell us something about dark energy as well. Cool. So, I'd like to take a second to tell you about a previous generation of weak lensing surveys. So this survey, which was called the Kilo Degree Survey, this is something I spent my whole PhD working on, and this was a ground-based survey. So it used the Survey Telescope at the VLT, which stands for Very Large Telescope. It's not a very imaginative name. And so that telescope, which is shown on the left-hand side here, that's it in the Paranal Desert in Chile. And this survey covered 1,000 square degrees on the sky. To put that in context, that's about 1/40th of the sky, or the amount of area on the sky that would be covered if you held up both your forearms to the sky like that kind of area. And you can see basically the area that was covered by the Kilo Degree Survey, or KIDS, wasn't the best acronym. Anyway, so this is the area covered, and what you're seeing here is that large-scale structure of the universe. So KIDS observed more than 27 million galaxies. They measured the lensing in those galaxies, and the lensing, the distortions in those galaxy shapes told us something about where the dense parts of the universe were and where the less dense parts of the universe were. So this is a map of density. The bright spots are very dense regions on the sky, and the black regions are basically empty parts of the sky. So what we're building here is a 2D picture of that cosmic web. And yeah, it took more than 10 years to do this survey. I'm going to show you an image, an example image from the KIDS group. It is okay to be underwhelmed by this image. That's kind of the point. So this is a black and white image, obviously. But what you're seeing in this image is stars, for example. Those are the spiky things. You're seeing a lot of galaxies. Those are usually the smaller things. You can also see the place where a big satellite flew across the image whilst we were taking the exposure, kind of ruined that part of the exposure, so thanks Elon Musk for that. But I want to highlight just a particular source in this image. So let's zoom in on that. So I don't know if this was a star or a galaxy. I think this might be a star. But let's be generous and say this is a galaxy. This is the type of thing we'd like to measure the shape of to try and get a sense of how much it's been distorted by gravitational lensing. you can see how pixelated this source is. You know, we've probably got, I don't know, 20 pixels to work from here. Imagine if we were using this galaxy just to the bottom left of it, that's like 5, 6 pixels. So we're working with really pixelized images of galaxies here. And yet we're looking for really tiny distortions in these 5 pixels that is caused by lensing. This is how challenging this measurement was to do. And this is one of the reasons you need as many as 27 million galaxies to do this well. Okay, so I want you to keep the image of this pixelized galaxy in your mind's eye as I go on to talk about a current or the new generation of weak lensing. So this is the survey that I work on now. It's called Euclid. This is the name of a space telescope that looks like that. That's it in the lab in Europe. It's about the size of a minivan. And this is it being launched into space from Cape Canaveral in July 2023. It was actually launched on my nephew's birthday, the day he was born. I said to my brother, maybe you should call your kid Euclid. He was pretty tempted. My sister-in-law was a bit less tempted. He's called Flynn. Okay. So, yeah, it's a space-based mission. That's why they launched it into space, of course. I was lucky to be there in Florida the day it launched. It was fun to be like... I'd only been working on Euclid about 2 months when I went to this launch. And it was fun being shoulder to shoulder with people who had worked on it for 15 years because they were absolutely bricking it that it would blow up on the launch pad. I was scared too, not quite as much, didn't have as much like skin in the game. So this is going to observe 13,000 square degrees on the sky, so that's 13 times more than kids who I just showed you. And that's about 1/3 of the entire sky. So in 1 year, it has collected more data than any weak lensing survey to date, surveys that took 10 plus years. And this is ultimately going to observe more than 1 billion galaxies, so between 10 and 50 odd times more than previous surveys. Okay, so what does the imaging of Euclid look like? I'm going to show you a video that basically showcases a small region of the Euclid survey that took about, a few weeks. So at the moment, you're not seeing Euclid's observations. This is it's actually from the Planck mission previously, and now it's just overlaying the region of the sky that Euclid will eventually observe. But for now, let's focus in on this little region of sky that Euclid has observed. And let's start zooming in. It's going to do a lot of zooming. Okay, so everything looks really, really nice. I downloaded this image onto my computer. I just started zooming in, like this is about to do. And the detail in it is basically incredible. So it's zooming in now on a galaxy cluster called Abel 3381. Let's zoom in some more. I think this is a bit where it gets really impressive. It just keeps zooming, and the details with which you can see the arms in this spiral galaxy. And you think it's going to show you this big one, and then it just keeps going into this little one. And even that one is really well imaged. So yeah, compare that to the 20 or so pixels we had to observe galaxies in the previous generation of surveys. And then zooming out is quite good as well, because you remember how far out you were to begin with. Yeah, and this is all made possible by the fact that Euclid is in space, basically, and it's got a better camera, but it is in space. And if you're in space, the light doesn't have to come through Earth's atmosphere to get to your telescope, and the imaging isn't disrupted by Elon Musk's satellite network. So it's it's pretty cool. So yeah, Euclid is going to have 1 billion galaxies imaged with that level of quality. The amount of data is kind of scary, really. Oh yeah, here's another one. Just in case that video didn't play, I've just got an image of another Euclid galaxy. It's absolutely unreal, the quality of it. So what is Euclid going to tell us, or give us? It's going to give us a 3D map of the universe that traces the last 10 billion years of its evolution. It's going to tell us whether lambda, this cosmological constant, is the correct description of dark energy, or does it evolve over time? So this was that thing that hit the front page of the BBC today. Like, it's going to have a definitive word, basically, on whether dark energy behaves the way Einstein saw it and the way we think it does in our standard model of cosmology, or if it's something different. Will these tensions between cosmological surveys be solved? Euclid is the most powerful cosmological survey to date. I think will have a huge impact on that debate and maybe settle it once and for all. And it's going to tell us, is Einstein's model of gravity the best description of the structure of our universe? Or is an alternative theory of gravity a better description of what we observe? So in other words, Euclid is going to tell us, is this recipe that we have in cosmology, is that a recipe for success or for disaster? Last thing I'll end on is cosmology is done by humans, and so I run the Euclid UK social media account, and this is us on Instagram. A thing I've been running is called Humans of Euclid, where basically I just interview all the cool people who work on Euclid and hear their stories, hear what makes them tick. So if you want to know more about Euclid, or specifically the people in Euclid, please follow this. It's on Instagram and Blue Sky. Used to be on Twitter, but a bit less active there now, because reasons. All right, that's it. Thank you.
Right, thank you very much. That was okay. So, anybody got any questions? Yeah.
Why is it called Euclid?
It is named after the ancient Greek father of geometry, and I think the reasoning for that was that it's kind of going to measure. Well, yeah, it's kind of going to measure the geometry of the universe. I don't even think this is one of its main science goals, honestly, but yeah, one of these ingredients or these free parameters of the universe is something that measures its shape, basically. Is the universe sort of flat or curved inwards or outwards kind of thing, but in 4 dimensions. I think that was something that was quite prevalent in the early discussions of what we want this thing to do, and I think it's less of a driving science goal now for this mission, but the name stuck, I think, because people liked it.
You mentioned, I think earlier, it was a European mainly project that was launched in the States, obviously, so is it a collaborative thing, or is it, how does that work? And who funds it? Who does the funding come from?
Yeah, so from you guys, I guess. Yeah, it comes from taxpayers across Europe primarily. So it's a European Space Agency mission. So I'm sure there's a pie chart of this somewhere, but I think it's mainly European nations who are the big financial contributors to this mission. And so that basically comes from taxpayers' money. It was launched in the States by SpaceX. I think originally the plan might have been to look for it to be launched by the Russians in maybe in Kazakhstan or in French Guiana, but then we fell out with them. So yeah, then it ended up being launched by SpaceX. So it can't be that mad, I guess, at Elon Musk. I can for other reasons, but won't go into this.
I was just wondering, what other things that we're looking for? I mean, is it going to look for like habitable planets, that kind of thing, with microlensing perhaps?
Yeah, so there is, basically the main science driving goals of Euclid are the cosmology side, so doing weak gravitational lensing and another measurement, galaxy clustering, that I didn't talk about today. But there are other sort of smaller groups within the Euclid consortium who are interested in stuff like habitable planets, who are interested in like high redshift galaxies, who are interested in some solar system stuff as well. I don't think it will be effective to detect planets via microlensing. I think because microlensing requires you to observe something for a period of time and then see, the brightness of something flare and then go away, caused by a planet going in front of it, I'm sure you know, which lenses the light from that object. And I don't think the observing strategy of Euclid is very conducive to detecting those kind of events. So I think if it's going to detect anything, I should look into the exoplanet group and find out what mode of observation they're trying to do to detect planets. I'm actually not too sure.
On the graph with the best fit line, you mentioned cold dark matter specifically. Why was that?
Yeah, good question. So, by cold dark matter here, what we mean is matter that doesn't move at high speeds close to the speed of light. So, essentially, when it became sort of apparent from observations that were like sort of mid 20th century, it became apparent that there was matter in the universe that was invisible, that wasn't emitting light. So it was already kind of known there was a lot of matter there, but the properties of that matter weren't quite clear. And it was only until sort of later that one of the properties, which is kind of the energy with which your average dark matter particle has, is quite low. So it's not like flying around at the speed of light the way, for example, neutrinos are. That's when that name comes from. Basically that, because it's quite slow moving, we call it cold dark matter. And the reason we kind of know it's slow is because if it was moving quickly, it would be too energetic to have formed the kind of large-scale structure that we see today. It wouldn't have clumped together through gravity and made these big structures because it had been too busy flying off around the universe.
If dark matter has got gravity, why does it not just pull itself all together? Because the universe mass is sort of expanding and not contracting or expanding too much. If dark matter has so much mass, why is it not pulled everything together?
So it has clumped together a lot to create this cosmic web. So when we do image the cosmic web, primarily what we're seeing is these galaxies, but they're tracing an underlying dark matter distribution. So that spider's web is mainly dark matter. But I guess maybe you're asking, like, why doesn't that web even collapse further into a big ball? So for one thing, I guess, if there was no dark energy in the universe, that would happen eventually, I think. So it would take time because everything was expanding outwards from the Big Bang. But without dark energy, that expansion would slow down because gravity would slow it down until eventually it would start collapsing. And then what you said would happen and everything would collapse back into a point, essentially. the reason that won't happen is because of dark energy. So, yeah, Einstein introduced this term to keep the universe static, so it perfectly balances gravity. What we now think is the case that is it overwhelms gravity, so the expansion of the universe is accelerating. That means it will never stop and it will never slow down, and essentially, yeah, all this matter will never collapse down because the space in between that piece of dark matter and that piece of dark matter is expanding too fast to allow it to happen.
So that would stop it clumping together and forming dark stars.
Yeah, so I don't know if dark matter... Yeah, so dark matter does clump together in places and could, I guess, create structures like that, but it won't do... All the dark matter in the universe won't collapse into one. Yeah, there'll still be spaces in between because those spaces in between matter are expanding really fast due to dark energy.
If you did have dark stars, you should have dark planets, so dark life and everything else.
Yeah, I need to think about dark stars and what that would mean in the context of dark matter. I guess just clumps of matter. Yeah. I guess it's hard to say would it be a star if it's not burning hydrogen to make, through nuclear fusion to make light. I guess that's kind of the definition of a star. So I might not call it a star myself, but yeah, it would create big clumps of dark matter. Yeah.
So I think the thing that people suggested in the past, they called these machos at one point, didn't they?
So yeah, machos was stands for massive compact halo objects, is that right? They were one of the contenders, and maybe some people would still say they are a contender for the identity of dark matter. I think really the leading contender for what dark matter is WIMPs, so weakly interacting massive particles. And these are basically particles that weakly interacting means that they either completely don't interact with things via electromagnetism, or if they do, it's very, very weak, or via the other forces. Basically, what WIMPs are particles that are flying through the universe all the time, through this room as we are standing here and passing through our bodies and stuff. But yeah, these particles are also clumping together in space and making these enormous dark matter structures. So yeah, WIMPs is the current leading contender. There's some observational constraints that I think actually microlensing. Who asked about that? Yeah, so microlensing, which is where normally a planet passes in front of something, lenses the light briefly and causes a flare in the light from that distant thing. That is one of the ways in which machos have kind of been ruled out, because if these massive objects, so kind of like black hole-sized clumps of dark matter were really floating around the universe all the time, we would see microlensing happening more than we do. So microlensing is one of the ways that this machos idea has been disfavored. We don't think it's like big clumps of dark matter or that are like just sort of dark stars and stuff like that. It's more likely that they are some weird particle that has never been detected in CERN or in any particle accelerator. That's the current leading theory, and those are called WIMPs normally.
In your introduction, you said basically that we were at a crossroad in cosmology, and basically Euclid is going to be our compass for the years to come. So what is your educated guess on where it will lead us?
That's a really, really good question. Yeah, I ask myself this every day, what do I think the future of cosmology will be? What are we going to find? Sometimes I'm a little pessimistic, and I think like, so for example, these kind of tensions that we're seeing, that could be a sign the recipe is wrong. It could be that there's mistakes in these analyses, and mistakes could just mean you've underestimated your error bars. So maybe these blue error bars should be a bit larger, and these red ones should be a bit larger, and they will overlap. And then we'll actually find that the recipe is right. Einstein was right all along. We have solved cosmology. Well, I say solved it, but I think, yeah, that could be sort of the solution, but it'll still lead us right back to we don't know what dark matter and dark energy are. And that's really a challenging place to be, because the dark matter particle, its properties are so loosely pinned down that it's really hard to know what to look for if you're a particle physicist, how to tune your accelerator to detect that particle. So it's quite different to the situation they were in with the Higgs boson, where the properties of that particle were really well established, and they knew exactly what to look for when they did that experiment. And they knew either we'll see it and standard particle of physics is correct, or a standard model of particle physics is correct or not. And that's basically, they saw it. And yeah, so we're not in that situation. And yeah, it's really hard to know how we'll, solve that particular issue if that's what we get to. I'm kind of hoping that, this thing that made the news today that says dark energy might be evolving, I kind of hope we keep seeing stuff like this, and it just keeps getting more and more perplexing, and maybe the answer to that will be a radical shake-up in our theory of gravity, for example. But yeah, I don't think we've got any sort of really strong contenders for alternative models of gravity either at the moment.
Yeah, right up at the back, yeah.
What's the time scale for the mission for Euclid?
It's like a 6-year mission normally, so the thing that kind of limits its operational time is it runs out of fuel, but it has fuel at the moment for about twice that amount of time, so it could potentially go much further into the future. There might be a sort of case of diminishing returns actually, because Euclid is observing so much of the sky already that there isn't too much more of the sky that would be useful for it to observe. The only parts of the sky it's really not observing are through the plane of our Milky Way, which you can't really see through because it's filled with stuff, and through the plane of the solar system, which those two things are inclined relative to one another, so they're different places on the sky. Can't see through that well either. So yeah, it could go on for longer, but I'm not sure if that would really generate loads of extra data on top of what the 6-year mission will return.
So where is it then? Is it sort of stationary in relation to Earth at the moment, or is it travelling just now? What's it doing?
Yeah, good question. So it's not like the Hubble Space Telescope, which was orbiting Earth and could be visited and fixed if necessary. Euclid is way too far from Earth. It's at a place called Lagrangian point 2, and it is not actually orbiting Earth, it's actually orbiting the Sun with us as we go round. So it's about 1 million miles, 1.5 million kilometres from Earth, and Lagrangian point 2 is a very special place in the universe where we like to put space telescopes. So the James Webb Space Telescope is there, and Gaia is there, and it's because it's like this gravitational sweet spot where if you put something there, then the gravitational pull of the Earth and Sun perfectly balanced with kind of centrifugal force as it goes around, and you don't really need to burn any fuel keeping it in this position. so you can use all your fuel to just do your survey. So yeah, that's where it is.
You mentioned, your job's a lot of statistics. How much of cosmology these days is, data, statistics, AI, and how much of it is, an Einstein or a Stephen Hawking sitting there thinking and writing down some equations?
Yeah, really good question, yeah. So, loads of cosmology now is statistics, huge data sets. It's basically data science. Statistical analysis, often aided by machine learning and neural networks and that kind of stuff. So, I don't know, if you're working with the data from the telescope, you're basically doing that kind of stuff. There's still lots of theoretical cosmologists. So my boss, the guy who I'm in a band with, is a theoretical cosmologist, and he was a pen and paper guy who is trying to do things like seeing results like this or results like this for the Hubble tension, and saying what could we do to gravity that is different from Einstein's theory that would generate something like what we're seeing here. And introducing all kinds of extra terms to those equations that might manifest in something like that. So that's still very much an active area as well, both theoretical and observational cosmology.
It's not at the point where you just ask the AI to do that
not quite, So I guess the challenging thing with the AI is it's very good at looking at something and emulating that, so copying it, but to sort of come up with something from scratch, I think that's the thing I think it would struggle with on the theoretical side, but it's really good at speeding up your analysis, for example. We use it a lot on the observational side.
I realise it's not going to be a recycle, but what's the end of life plan for something like Euclid, which is out in the L2 point? And can the L2 point get full?
I think it can get full. It's got 3 or 4 telescopes there already.
We're going to have a space station there. We're sending astronauts there next year.
I don't know. I don't know if it can get full. I only learned about this kind of thing when I started working on Euclid. But I think the plan might be to save a tiny bit of fuel to jettison it away from L2 when it's finished. I think that's the plan anyway, don't quote me on that. But I think it is good to not have too many things in that bit of the neighbourhood, because there are other constraints for that point in space that as well that you want your telescope to satisfy. So for example, it isn't just staying in a particular spot, it's actually orbiting that spot in a small orbit. And the reason you want it to do that is because if it was at the exact L2 point, it's actually in the Earth's shadow as it goes around the sun. And that means its solar panels, so it's got fuel, but it's also got solar panels, would never see the sun. That's not good. So what you want it to do is kind of just go around that L2 point, occasionally coming in and out of the Earth's shadow so it can see the sun. So all of the telescopes at that point want to do that as well. So they all have to be in these orbits and make sure that they're outside of each other's orbits and it's not too crowded. So I think that's why you would want to kind of not just leave junk there and kind of jettison that way.
Okay, well, thank you very much. It's been absolutely fascinating tonight. And if we can give us a vote.